Section 7.5 of Pure 2, Year 2 book, Chapter 7, Simplifying A cos plus or minus B sine. We're going to rewrite it as a single trigonometric function using addition formulae. Now the book provides you with what formulae to use in what situation. However, it will become very obvious once you start doing that you won't need to memorize too much of this information. So what we're going to do, we're going to replace this sum or difference either as r sine of x plus or minus an acute angle alpha, and r is the constant that's always positive, or as r cos x plus or minus alpha. So there's two different guises. The best thing to do right now is to just have a look at the example, so you see that it won't be necessary to memorize these results, and it will be quite intuitive as to how to approach questions individually. Okay, so example 14, you are asked to show that you can express 3 sine x plus 4 cos x in the form r sine x plus alpha, where alpha is an acute angle and r is positive. And this for part B, you can also express it in terms of cos, r cos x minus alpha. So the sum of sines and coses can be represented by a single sine or single cos that's simply just shifted, stretched, transformed. Okay, so the first thing you need to do is to rewrite this using addition formula. So it's going to be, and I'm going to expand that addition. So let me just remind you, sine A plus B is equal to sine A cos B plus cos A sine B. So we're going to use this addition formula, and I'm going to times it straight away by r to obtain r sine x in this case, multiplied by cos B, and then r cos x, that was alpha, sine x multiplied by cos alpha, and then cos x multiplied by sine alpha. This has to be made equal to our expression, so 3 sine x plus 4 cos x. I like to write these underneath each other, and you could see clearly that the way I've done it, you've got sine x underneath sine x. So for these two expressions to be equal to each other, whatever is sine x is multiplied by needs to be equal to 3. So it's multiplied by r cos alpha, and that's equal to 3. For the second one, you've got cos x over here. This is r sine alpha that multiplies cos x, and over here it's multiplied by 4. So these have to be equal. So the way to find your alpha, you're going to divide your r sine alpha by r cos alpha, and obtaining tan alpha, because r will cancel. For the first time, as I'm doing it, I'll show you that this is the case. So that clearly cancels, and you've got 1 sine alpha over 1 cos alpha. But what have I divided? Well, 4 divided by 3. A common mistake is when you do it quickly is not to check and do accidentally 3 divided by 4, and that would obviously not gain you in correct marks. So that's 4/3. So alpha is tan inverse of 4/3. We are in degrees because you could be in radians, is 53.3 degrees to 1 decimal place. They will also tell you what accuracy to round this angle to. It's quite common for the degrees to be 1 decimal place, for radians up to 3 decimal places. So we also need to find what r is. So r, as quoted before, is going to be equal to these, like Pythagoras, 3 squared plus 4 squared square rooted. Now let me explain to you where it comes from, and I will only do it once. So imagine squaring the r sine alpha. So if I do r sine alpha squared, and then add to that r cos alpha, which is squared, what I'm going to get here is r squared, and then you've got sine squared alpha from this expression, and then plus r from this term, and r squared multiplied by cos squared alpha. If you factorize r squared, you'll be left with sine squared alpha plus cos squared alpha in brackets, and that's clearly equal to 1. So that will be equal to r squared. But what have we got here? We've got r sine alpha, which is your 4 squared. So r squared is going to be equal to 4 squared, and then r cos alpha is 3 squared. Add them together. That's going to be 16 plus 9, which is 25, giving me r equal to 5. Because it's positive, you don't take the negative root. Okay, so let's now put these r and alpha together. So we are going to write the answer as 5 sine x plus 53.1 degrees. So that is the replacement for our sum. Okay, we can also change this into causes. It will be exactly the same, because if you imagine sine and cos being transformed in a clever way, they could overlap. So you start in exactly the same way. Expand this using addition formula for cos of a minus b. So remember, in this situation, you've got cos a, cos b, plus sine a, sine b. So let's expand it. You've got r cos x, cos alpha, plus r sine x, sine alpha. So that has to be compared with our expression, which is 3 sine x plus 4 cos x. So over here, you need to watch it, because sine x is not in the first term of the expansion, but it is over here. So if you compare this with this, I'll be getting r sine alpha being equal to 3. And if I compare this with this, I'll be getting r cos alpha is equal to 4. So tan alpha is going to be sine over cos, so it's 3 over 4. So alpha is equal to tan inverse of 3 over 4, and this time it's 36.9 degrees. R squared is simply equal to sine squared r sine alpha all squared plus r cos alpha all squared, so it's 3 squared plus 4 squared. So r is again going to be 5. So the second replacement for our 3 sine x plus 4 cos x is 5 cos x minus this times 36.9 degrees. So this is example 14. So we've got example 15. In this example, we have to show that you can express sine x minus root 3 cos x in this form. And then we're going to sketch it. Obviously, r is always positive and alpha is going to be an acute angle. But this time, they tell me that alpha needs to be between 0 and pi over 2. This informs me that I need to work in radians. Okay, so the method is going to be the same. The first thing we need to do is write the expansion. This one is sine a minus b. So we're going to write it as r sine x. Remember, sine and cos get together, so cos alpha. This time, if it's a sine expansion, minus is going to occur. Cos x and then sine alpha. This has to be equal to our sine x minus root 3 cos x. Let's compare. So over here, I've got sine x and sine x. You've got 1 sine x, and that's equal to r cos alpha. Over here, you've got cos x and cos x. Over here, we have r sine alpha equal equals to root 3. Tan alpha is going to be your sine divided by cos, so root 3 over 1, giving me alpha being tan inverse of root 3, which is a lovely angle of 60 degrees or pi over 3 in radians. R is going to be 1 squared plus root 3 squared, let's say that's r squared, so that's equal to 4, giving me r is equal to 2. Putting these together, I will have 2 sine x minus pi over 3. So if you ask to sketch this function, you just need to, they don't tell me what on what domain to sketch it, so we just make sure that it's quite big. So this one here is stretched by 2, because there's 2 outside, and it's going to be shifted 60 degrees right. So we're going to move our sine 60 degrees right. So normally sine looks like this. There is your pi, 2 pi. We're going to imagine it's stretched. We're going to shift it. So this is pi over 3. This is 2 pi over 3. 2, 3, 4 pi over 3. And 5 pi over 3. And this one is going to be 2 plus 1 third is going to be 7 pi over 3. So we'll stop there. Okay, so that point will go over here. This point, which is actually at 3 pi over 2, is going to be shifted over here at 5 pi over 3. And this is, which is at pi over 2, will be shifted to 2 pi over 2. And then over here, we're going to move to pi over 3. So this point here, which was at pi over 3, will move onto the origin here. So, so y-axis. There you go. Okay, so this point here is going to be at 2 pi over 3, 2. This point here is 5 pi over 3 minus 2. You could also work this value, but I don't think you've been asked to do that, so we can leave that. So it goes through pi over 3, 4 pi over 3. I've gone to more detail than necessary, but it's always a good idea to actually find that point so we could find it. So this is when x is equal to 0. Your y is going to be equal to 2 sine, putting 0 into this, of minus pi over 3. So that gives me 2 times negative root 3 over 2, which gives me negative root 3. So that point here is negative root 3. Okay, we're going to move on to example 16, which I had not jotted down, so not a problem. We'll come back to example 17, do them in order. So example 16, part A, will have 2 cos theta plus 5 sine theta. This time we are going to express it as Rcos theta minus alpha. Remember, notice that if we're changing into causes, there is a plus between the two terms. We have to use the one with a minus. And then we are working in degrees this time. So let's express this in expanded form. So r cos theta cos alpha plus r sine theta sine alpha. Let's compare these. So cos theta is cos theta. So whatever cos is multiplied by, they need to be equal. So r cos alpha is 2. Sine theta over here, r sine alpha gives me 5. So tan, carefully check that you're dividing correctly. Sine over cos, 5 over 2. So alpha must be the inverse of tan, which is 5/2, and that gives me 68.2 degrees. The value of r is 2 squared, so these are those numbers here, added together. Let's square root it this time straight away. That gives me, let's write it in, leave it in exact form, 4 plus 25, 29. Very often, if r is a third, you leave it in exact form, in fact, all the time. But in terms of the thinking about the angle, you can't, if you can't, you've got to round it, okay? If you can't give it in exact form, that refers more in radians, or you have to do it in terms of pi, then you do that. Okay, so now we have to solve, and it says hence, we are going to solve for theta being between 0 and 360 degrees. The following equation, 2 cos theta plus 5 sine theta. So those expansions, you know, the sums, when they can be written together as a single function, this is a nice application of why we need to do it, because of being able to solve those type of equations. So over here, what has this got to do with part A? Well, I have just found the replacement for this. I didn't write it down separately, but I will do it now. So this is cos theta minus 68.2 degrees. So the left-hand side can be replaced with this. So root 29 cos theta minus 68.2 is equal to 3. So cos theta minus 68.2 degrees is equal to 3 over root 29. Okay, so theta minus 68.2 degrees is equal to cos inverse of 3 over root 29. Notice we are solving for theta shifted 68 degrees to the right, so we should really adapt our range of values for which we are solving. So this is going to be up to 360 minus 68.2, which gives me roughly, you know, it doesn't matter if I keep it up to 360, it's this bit that's important, which won't really affect our question too much. Okay, so do the cos inverse. You're going to find the angle of 56.1 degrees. There you go. So rearranging this, actually we need to go up to the other one, because remember cos, so we need to have plus or minus 56.1 degrees. If we go for the next one, which is 360 minus 56, we won't reach that end point, so that's okay. These are the two solutions. So theta is equal to 56.1 degrees plus 68.2, or the second one, 56 minus 56.1 plus 68.2 degrees. Okay, so these are the two solutions. If you did go for the one that's 360 minus 56.1, which is not wrong to do it, just to demonstrate that it's not going to get you outside the range. So this is going to be 303.9. Okay, so if this is our angle, you could see that here the range of values that we were solving for was 291.8 degrees or thereabouts. Well, this is outside the range, so you don't need to worry about this second solution. But we did obtain the second solution by considering the angle on the left-hand side of our principal angle. So let's state these. If you add these two together, that will generate the small answer. That should be 12.1 degrees. If you add these two together, you'll have big answer, 124.3 degrees. This is to 1 decimal place. So this is the, again, common question. Common question number 1 was to sketch the graph. The second one is to use in solving equation. And the third way of using this is to help you identify the minima and maxima of that function. So here we've got this function, and we are working in Well, let's work in degrees, okay? So we are going to expand that function, express it in terms of r cos theta minus alpha. So straight away incorporate r. Okay, so we'll write this one underneath since it's too far away. There you go. So we've got cos theta over here, so r cos alpha is equal to 12. And r sine alpha, if you think about cos, some people cross it off and then see what's left behind, that's 5. Divide sine by cos to obtain tan alpha. That gives me alpha being tan inverse. Okay, tan inverse of 5 over 12 gives me the angle of 22.6 degrees. So just need to find r, 12 squared plus 5 squared. Square rooted, that is 144 plus 25, square root of 169, which is 13. So our function f of theta can be rewritten as 13 cos theta minus 22.6 degrees. So to find the maximum value of this graph, so you just don't need to sketch it every time, but just to demonstrate. This is your cos graph shifted and stretched, shifted to the right. Let's start again. So it's over here normally, so it's maybe something like this. Okay, so that maximum is shifted by 22.6 degrees, and that's 13 and that's minus 13. So you can see from the graph that the maximum value cos that's been stretched by the factor of 13 will be 13. So f max is 13. When does it happen? Clearly, you can even now, if you sketched it, you can read it from the graph. But there you are asked for the smallest positive value, and it is the smallest positive value. The way to find it in algebraic way, you just need to make your function equal to 13, so your f of theta equal to 13, and solve that equation and pick the solution that will give you the smallest positive value. So it's really quick, because that has to be equal to 1, because cos is at its maximum when it's equal to 1. And when is that equal to 1? Where theta minus 22.6 is going to be equal, well, cos is 1 at 0 and then at 360 or minus 360. So you add 22.6 degrees to give you 22.6 degrees and then 382.6 degrees, but that's too big. This is the smallest. So the answer is theta is equal to 22.6 degrees. So function reaches maximum of 13 when theta is equal to 22.6. Okay, that leads us to exercise 7e.